We have talked about the use of printed circuit board to make transmission line, such as microstrip line, strip line, and coplanar strip line. This strip line can be used as transmission line. In addition to that, they can be used to make special components. These are some examples. We can design a transmission line either using microstrip structure or strip line structure or some other structure by controlling the line width and the spacing between the strip and the ground plane. We can get the desired characteristic impedance jack knot. Now by using a microstrip line with a length of lambda over 4, we can make a transformer. This transformer is called a quarter wave transformer. Like the transformer at low frequency application, we can transform a voltage from a small voltage to a large voltage, or from a large voltage to a small voltage, or in other words, step up or step down, using this quarter wave transformer. Now when we perform this step up or step down of voltages, at the same time we are also doing step up or step down of the impedance. Based on the transmission line equation that we have, the input impedance at a certain distance away from load impedance jack L is given by this formula. So notice that if the length jack prime is quarter wavelength and beta is 2 pi over lambda, we get beta jack prime to be equal to 90 degree, or pi over 2. So tangent pi over 2 will be equals to infinity. So therefore jack L will be negligible compared to this second term. The same goes for the denominator, where jack naught is negligible compared to the second term. So therefore this equation gives us jack naught square over jack L. So notice that the impedance jack L is transformed to jack in, which is equals to jack naught square over jack L. In other words, the impedance is inverted from jack L to 1 over jack L. So a quarter wave transformer is also called a impedance inverter or admittance inverter. In this case, we see that the impedance jack L is not only inverted, it can be transformed to another value, jack in. The value of jack in that we want can be controlled by controlling jack naught. Different value of jack naught will give us different value of jack in. Therefore, we can do step up or step down of the impedance. In the design of a quarter wave transformer, we can use this formula which is the rearrangement of this formula here. Another application of printed transmission line is to construct a inductor or a capacitor. Similarly, based on the equation for input impedance, now this time the length is not quarter wave length, but any length other than quarter wave length. If the transmission line is shorted at the end, we have jack L equals to 0. So if jack L is equal to 0, this equation gives us input impedance given by J jack naught tangent beta jack prime. Compare this with J omega L. We see that a transmission line shorted at the end is equivalent to an inductor, where the inductance can be found using this equation. And we can get any inductance that we need by controlling jack naught or by controlling the length of the transmission line. Similarly, we can make a capacitor by using a transmission line open circuit at the end. Based on the equation here, in this case, jack L is infinity. So if jack L is infinity, the input impedance will become an equation that looks like this. So comparing this equation with 1 over j omega c, we see that we can get any capacitance that we need by controlling the characteristic impedance or admittance and also by controlling the length. We can change either the characteristic admittance or the length of the transmission line or both to get the capacitance that we need. Another application of printed transmission line is to make a resonator. In this case, we use a transmission line which is either half wavelength or quarter wavelength. The transmission line can be shorted at the end or open circuit at the end. Consider the transmission line with a length of half wavelength or multiple of half wavelength shorted at the end. From transmission line theory, we know that impedance repeats every half wavelength. So that means 0 ohm at the end of the transmission line will be transformed to 0 ohm as well at the input of the half wavelength transmission line. But this only happens when the length is exactly half wavelength. In other words, when the frequency is slightly higher or slightly longer, slightly higher or slightly lower than the resonant frequency. That means the wavelength is slightly shorter or slightly longer than the length of the transmission line. The impedance will be larger than 0. In other words, we have a series resonance characteristic where the impedance is 0 ohm at exactly the resonant frequency, but it is capacitive or inductive at a frequency higher or lower than the resonant frequency. We can then represent a halfway blank transmission line shorted at the end with an equivalent circuit of a series LC network. That is a series resonator. For the same halfway blank transmission line, if we leave the end open circuit, similarly, infinity ohm will be transformed to infinity ohm halfway blank away. So we get infinity ohm at exactly the resonant frequency, but when the frequency is slightly higher or slightly lower than the resonant frequency, the input impedance will be lower than infinity. That gives us a parallel resonance characteristic. In other words, we can represent a halfway blank transmission line open circuit at the end with a parallel resonance circuit. If the length of the transmission line is a quarter wavelength or odd multiple of quarter wavelength, the situation will be different. In this time, if the quarter wavelength transmission line is shorted at the end, it will be transformed to infinity ohm at the input. This is the behavior of a quarter wave transformer, but this time we have a short circuit at the end. So 0 ohm is transformed to infinity ohm. Similarly, we only get infinity ohm at exactly the resonant frequency. If the frequency is slightly higher or slightly lower than the resonant frequency, we will have lower the impedance lower than infinity. That is the behavior of a parallel resonant circuit, which can be represented by a parallel LC network. And if a quarter wave transformer is open circuit at the end, infinity ohm will be transformed to 0 ohm. That is the behavior of a series resonator, which can be represented by an equivalent circuit consisting of inductor in series with a capacitor. The use of transmission line to make resonator is advantageous at microwave frequency because we can get a much higher Q than the construction of inductor in series with capacitor or inductor in parallel with capacitor. In terms of physical implementation of resonator, if we were to use an inductor in series with a capacitor, we can use a thin line to make an inductor, and using an interdigital structure to make a capacitor. However, as we mentioned earlier, this series inductor and series capacitor will give us a resonator with much lower Q. The same goes for parallel resonator consisting of an inductor made from a thin transmission line and a parallel capacitor made from an interdigital structure. The Q will be very low. To get high Q, we need a transmission line which is short-circuited at the end or open circuit at the end. This is an example. This is a transmission line with a length L and width W, open circuited at both ends. So it behaves as a resonator. Alternatively, we can use a ground plane which is defected with a hole, with a hole which has a width W and length L. The effect is the same, that is, we get resonance behavior. We can also make a resonator using a ring-shaped microstrip line or a ring-shaped defected ground. We can also use triangular patch or circular sector patch to make resonator for different applications. Resonators are used in the design of bandpass filter and bandstop filter. This is the example of a bandpass filter where we have a series resonator followed by a parallel resonator and then followed by a series resonator. To make a bandstop filter, the configuration will be opposite. The series resonator can of course be replaced by a transmission line structure, open circuited at both ends or short circuited at both ends. The same goes for the parallel resonator. It can be made using a transmission line, open circuited at the end or short circuited at the end. The coupling from one resonator to another resonator can be done by a gap between them, which gives us a kind of like a capacitive coupling from one resonator to another. The selection of the resonator the combination of the resonator can give us different kind of frequency response. For example, we can in a particular selection of resonator, the combination of the three, we can get a Butterworth bandpass filter where the frequency response is flat in the pass band. However, for a Butterworth filter, the roll off is slower. In a bandpass filter, the transmission line, the transmission coefficient is 0 dB in the pass band, whereas the reflection coefficient is negative 60 dB or more in the pass band. Low reflection coefficient means there is very little reflection because most of the microwave energy is transmitted. Whereas in the stop band, most of the EM energy is reflected, therefore reflection coefficient is close to 0 dB and the transmission coefficient is very low. With a different selection of the resonator combination, we can design a different bandpass filter. In this example, we have a Chebyshev bandpass filter. The feature of this filter is that the roll off is much faster than the earlier Butterworth filter. However, the shortcoming is, or the trade-off is that there are some ripple within the pass band. However, so long as the ripple is not too high, it is advantageous to have a faster roll off. Similarly, in the pass band, the transmission coefficient is close to 0 dB. Of course, we get some ripple within the pass band, and the reflection coefficient is very low within the pass band. This is an example of a bandpass filter using capacitively coupled series resonator. Each of these resonator is a half wavelength transmission line open circuited at the end. The coupling from the transmission line to the resonator is through a gap, which is equivalent to a series capacitor. Similarly, from one resonator to another resonator, the coupling is done through a gap, a series capacitor. The more resonator we use, the higher is the filter order. That means the faster is the roll off in the stop band. This classic directly coupled bandpass filter consists of a series of half-wave resonator spaced by capacitive gap. The special features of this kind of bandpass filter is that the bandwidth is very narrow, and it has superior stop band rejection. Another type of bandpass filter is the parallel coupled microstrip. In this case, similarly, we have a half wavelength resonator open circuit at the end. Or we can consider this resonator as two quarter wave resonator connected together, each having a different line width. From the transmission line to the resonator, the coupling is done through a gap. However, this time the length of this gap is the quarter wave length. So we have a longer coupling length. That means the spacing can be wider to get the same amount of coupling. The same goes for the coupling between one resonator to the next resonator. As we said earlier, because the coupling length is a quarter wave length, the spacing can be wider. With wider spacing, the bandpass filter is easier to make because the error in the gap width is not so critical. The advantages of this parallel coupled microstrip bandpass filter is we can implement a filter with a wide range of bandwidth. It can be designed to have narrow bandwidth or wide bandwidth depending on the application. We can make use of the bandpass filter to make a Diplexer or a Duplexer. A diplexer is typically the same as a duplexer. The difference is only in terms of the application. A diplexer is to split two frequency into separate channel. For example, the inputs we have an input signal with two frequency, F1 and F2. Bandpass filter with a center frequency of F1 will allow only F1 to pass through and be transmitted to the receiver, and the second bandpass filter with a center frequency of F2 will select the second frequency to be passed to a different receiver. This is the operation of a diplexer. In the case of a duplexer, the circuit is the same, but the application is different. In a duplexer, what we wish is to transmit and receive at the same time. In this case, we imagine this terminal is connected to an antenna to transmit and receive signal at the same time. The signal to be transmitted is F1 and the signal to receive is F2. We can connect the transmitter F1 to this terminal. The signal will be transmitted to the output and not to this third terminal, which is connected to the receiver. But when the antenna receives a signal with a frequency of F2, this signal will be transmitted to this second channel due to this bandpass filter with a center frequency of F2. In the design of diplexer and duplexer, not only we need two bandpass filter with different center frequency, typically we will also need quarter wave transformer to improve the performance. For example, as far as F1 is concerned, if the signal frequency is at F1, the transmission coefficient is close to 0 dB. That means we have a match impedance at this point. And that means as far as F1 is concerned, we will have maximum power transfer. When the signal frequency is F2, bandpass filter with a center frequency of F1 will have a reflection coefficient close to 0 dB for F2. That means the input is similar to a short circuit or open circuit. Imagine if we have equivalence of short circuit at this point because the reflection coefficient is 0 dB. A short circuit is transformed to open circuit at the other end, or infinity ohm, by the quarter wave transformer. That means frequency F2 will not be transmitted into this quarter wave transformer because of the infinite input impedance. In other words, all the microwave energy with a frequency at F2 will be transmitted to the second bandpass filter with a center frequency at F2. Similarly, if the frequency is F1, the input impedance of the second bandpass filter will be either very high or very low depending on the design. In other words, the reflection coefficient is 0 dB at F1. Imagine if we have equivalent of short circuit at this point. Short circuit is transformed to open circuit or infinity ohm by the quarter wave transformer. So therefore, a signal from the transmitter will be transmitted to the output, and none of it is transmitted to this second channel. That prevents the transmitter signal from going to the input of the receiver, but all the transmitting signal will go to the antenna. Similarly, we can design a multiplexer instead of a diplexer with one input and multiple output. That means we will need n number of bandpass filters, each with different center frequency.